una vez ya. Prometo no hablar.
Okay, good morning today. Welcome to the conference for this morning. It's a pleasure for me to introduce the Professor Alberto Berkowski, who will be to talk about some geometry and arithmetic on quaternion manifold.
Well, of course, I want to start as usual, thanking the organizers and especially thanking honor and to be here in celebration for Pepe, who was my boss, my collaborator, and last but not least, my friend. You know, so it's a very good friend to everybody. So it's a pleasure. Eh? Yeah, exactly. And my students. Yeah, exactly. So I'm going to talk something that has been fascinating. Oh, no, se me olvidó. No, ya lo había aprendido, ¿verdad? Ya lo habías aprendido, ¿no? No funciona. Bueno. ¿Cómo? Creo que no lo aprendiste bien. Bueno. O hablo. Bueno, muy bien. Lo cambiamos. No, pues una vez felicitando. So I want to speak about something I've been fascinated with doing geometry, dynamics, arithmetic, many things over the field of the commutative field of the quaternions. And so let me recall you a few things that most people know, but maybe for the young people. So suppose you have a finite extension of Q, so a number field. For simplicity, I'm going to take a quadratic field which has the property of being totally real. So all embeddings in C are real, all line the real line. So as an example, I'm going to take this canonical thing, Q. So this is simply as a field is simply that. Or real numbers of Q1 plus square root of 2Q2. And this field contains a beautiful ring, the field of ring integers of this field is O, equal O of that. So let's call this, and let's call it ZK. Carry the property that Q1 and Q2 are integers. Because the objective is to try to study or generalize to quaternions one of our favorite objects. I'm sure it's not mine, only mine. It's the best friend of everybody, is the modular group. So this is one way of the form. D are integers, and determinant AD minus BC equals to 1. And we all know all this history. We know their math, modular curves, cryptography, etc. No, I don't want to talk about that because everybody knows a beautiful subject. And my objective here is what happens if I try to change A, B, C, D in quaternions. And what do I mean by a discrete subverse of that? So it's a natural question. It's been originated, maybe. And in particular, this will have, for instance, this. We know it's Lie algebra. We know it's the tangent unit circle bundle of the hyperbolic plane. It's a three-dimensional Lie group. Has fantastic foliations. Contain lots of arithmetic. In fact, the Riemann hypothesis is a consequence of ergodic properties of that. And so I also try to do the second part. Students, Elena and Carlos, but I want to speak about that. The Sagier-Sarnak analog of that with the foliations, beautiful foliations that are, but I won't be speaking of that. I won't be speaking of the geometric part of that. So this is, and so of course, natural quadratic field, real quadratic fields, one natural group to consider is this one. And so these are n1 plus square root of 2 n2. We can take any d, but I take 2 just as a, and then you can immediately see that this group is not discrete. I remember when Parker gave his conference here, see, this is obviously discrete in SL2Z because coefficients are integers and you cannot deform it, no? No, I remember he saying, when he was young, of course, John Parker is here, he thought it was a very complicated. No? Yeah, I'm talking your story. No, I say John Parker. I say John Parker, I say that. It's an obvious thing, no? But these things, kaput. Because you see matrices of this form, by chronic square root of 2 is irrational. This is dense in the reals, so there's no discreteness. And so what do we do about that? And so I'm sure everybody knows about it, but there are young people in the, not in the first rows, but in the, after the third row, because they can't hear well. No. Okay, so, no. And so Hilbert had a fantastic, he thought about how to fix that. He said, why don't we take 2 copies of because this group on hyperbolic, real hyperbolic plane. And we use images of the modular, or if I say that, everybody understands what I'm talking about, right? Exactly, no? Well, anyhow, Hilbert thought, well, we take 2 copies of the hyperbolic plane. Hyperbolic plane considered as the complex numbers with imaginary part strictly positive. We take 2 copies. There's this act of PSL to Z. PSL to Z act on the first factor and act on the second by applying Galois operation, which simply means change n1 plus n2 square root of 2, change the signs of n2. And then you can show that now the action is, now you can see it's a discrete group, okay, like John Parker thought when he was a young student, not so long ago. And then you can see that I will have now a manifold model on H cross H. It's not reduced, a beautiful manifold, and then you show that has finite volume. And then people like Hirzebruch, well, okay, anyhow, this is Hilbert's, but Hilbert didn't write that. He gave it to his student Blumenthal. And Blumenthal wrote his thesis. And later on, people forget that Blumenthal actually is the one that did with the idea of Hilbert. No? And so that's why you allow me to put the name Blumenthal to the name. And in the case of the complex, I start with the complex case because now you have an algebraic surface. You have to prove that it's algebraic, so you have an algebraic surface. And it's actually a singular orbifold because you see, obviously, here, and that this has torsion, 2 torsions, 3 torsions. The first 2 primes are my favorite, no, 2, 3. And that means that we'll have conic points, will be an orbifold. And then it will be not compact, but it will have at infinity a section. You see the orbifold, one of my favorite, take my special Japanese, Korean chocks, which I don't share. And here is the union. Is if you take the group is that you know very well the line, the vertical line with the minus one half. And you have to grow this with this by 180, and that with that, and you get that corunda. Corunda is a Mexican name of a cake in Mexico with 3, you know, the culture of Mexico, no? With 3 picos. And, well, but what is horizontal are tangent at infinity, are circles, and in the case of H cross H divided by the modular group, the cross section for square root of 2, a famous manifold is the manifold. Wait. 2, 1, 1, 1, the famous cat map, or whatever you call it, is an automorphism of the torus. It's the torus S1 cross S1. This is an automorphism of this group. And you suspend this map, you have a manifold dimension 3 with solvable geometry. And a quotient, final quotient of that is what is the cosp. So you have this tiny circle with a beautiful Anosov 3 manifold, well, up to final cover, orbital cover. And so that implies that it must have lots, since these objects are beautiful, must have something beautiful. And then what Hirzebruch did, and because Pepe is a singular man, Hirzebruch compactified the Hilbert-Blumenthal surface, and then he made the resolution of singularities and obtained in the classification of Kodaira some of the most beautiful objects is the singularized Hilbert-Blumenthal surface, which contains enormous quantity of beautiful things. So now that's the introduction to my talk. I want to see if I can do something in that regard, but with A, B, C, D are now quaternions. And of course, the non-commutativity will, well, let's see what happens. And so, this is joint work with Adrián Centeno, who's now is a very good young mathematician working at CIMAT now. And I won't talk of the second part. And I can see one of our collaborators there is of this paper. This talk will be based on these papers. So Adrián Centeno is in CIMAT. Is a young Joe Quinn. I got a theorem of that. And then this one is the beginning. This Juan Pablo Diaz is sitting there with a metallic yellow shirt, so you can localize it very easily. And so this is what I'm going to talk about. So, okay, so let's start by giving basic definitions. So we consider a quaternion algebra and review some classical facts. So what's a quaternion algebra? First, you take a field K, any field, but we require to have characteristic 0, although you can do it in other cases. And then a K algebra, quaternion algebra, if you have 3 beautiful elements which are mimic the famous Hamilton quaternions, Ij that satisfy these things. You take 2 non-zero elements of the field, A and K, A and B, and require that I squared be A and J squared be B. But A and B could be positive, negative, one positive. Well, if Q is the reals, if the field is the reals, and A and B are both -1, you have the classical real four-dimensional quaternion algebra, one of the few division algebras which we know. But you can use any field. So the idea of my talk will be to replace K by a total real field. And I will specifically think of quadratic fields for simplicity of my talk. And so this is the definition of the object. This is the algebra we're talking about. So here's what I told you. If K is the real field, and notice that here you have a bold I and a bold to distinguish the Hamilton and the ones of the algebra. And we know that the quaternions have these 2 involutions which are canonical, which are conjugation, which means the generalization of complex conjugation, change the sign of all imaginaries, and the norm, which is actually the square of the norm, metric norm that we are used to, is Q times Q bar. And the places where these are 0 are very important. And the trace is 0, there is a trace minus. When the trace is 0, it means that you have pure quaternions. And in the case of Hamilton quaternions, B bar is B, where I haven't, sorry. This is the space of quaternions whose real part is 0. So it's a 3-dimensional. In the case of Hamilton, it's simply the quaternions which are pure. It's R3 with our basis ijk that probably the young people don't know. When you take vector calculus and use ijk, it's because of this reason. And of course, when the norm is equal to 1, you have the quaternions which of norm equal to 1, which is the unit sphere S3. And because we have no commutative group, which is if you remove the 0, the unit is the whole space H. The H for Hamilton will be that. I always had the impression they stole the H, the quaternionic people stole the hyperbolic H, our hyperbolic H, but then I get used to it. No? So this is the real H, the Hamilton H. Okay, so the field the trace of Q is E plus E bar. It's 2 times the real part. What? This? It's a trace. I defined it in the previous page. It's Q plus Q bar. Q plus Q bar. It's E plus E bar. It's the real part. But 2 times that. Two times that, because you always forget to divide by 2 by the 2 times that. No? So, but it's important because that means that if you remove 0, because it's a division algebra, it's a non-commutative group, and if you restrict it to unit sphere, this group is the unity sphere as a group is SU2. I mean, there. And it double covers via this map, it double covers, SU2 double covers the orthogonal group. And this quaternionic notation gives you instants. So these are things to have in mind, no? The unity sphere, and okay. Now I come to this object. I want to define that, remember. So well, now you consider the space of all 2 by 2 matrices, but with quaternionic entries. This means that it acts linearly on H cross H. But since it's not commutative, you have to talk about left module or right module. There's the notion of right line. You take a non-zero point, and you multiply by lambda, non-zero on the left, and you have left line, you have left straight lines, right straight lines. But anyhow, so this is a matrix with entries A, B, C, D, and it makes sense to speak with this as, I will speak later, a notion of determinant due to Alillois, Dieudonné. Jean Dieudonné from which country, which city in France? Lille. Jean Dieudonné, Lille. Where's his pharmacy? La Grand Place. No. I know more of Lille about you. You forgot. Well, anyhow, it doesn't matter. Okay. Eh? But yeah, Jean Dieudonné, Lillois. Si, oui, d'origine. Voilà, c'est pour ça que je dis ça. So I take matrices like that, acting on the left or right module, according to your tastes. And, of course, the Möbius transformations are like this. We restrict A, B, C, D to be complex, to be integers. That's called the Möbius group. It's the isometry, so H3 is PSL to C. And I want to define PSL to H. So, but first I define this set of, you can think of this, I mean, how many parameters you have? 4 times 4 is a 16-dimensional space of matrices. Is a vector, real vector space of dimension 16. And then using a notion that I will explain later, Dieudonné determinant, it makes sense the invertible, and that's our group of matrices, non-singular matrices. And then, with this, you can construct the Möbius transformation, copying, mimic line by line, the idea by Gauss, no? This formula. The only caveat is that 8 on the left is like the Mexican politics. 8 to the left, and this one to the right. Sorry, one mistake, but it's AC, AQ plus B times on the right, CQ plus D, and the inverse on the right. Okay? And that's a beautiful object, of course. What happens to infinity? No? And so you have H4, which is as a space is R4. You can compactify one point at infinity, and you have S4 at a Riemann. And then you define a point at infinity that way. And so now you construct, you can prove that this forms a group of dimension 10. I will explain why. And it's exactly, by a explicit formula, it's exactly the set of transformation of S4. Once I decided, well, I give the definition for the point at infinity. It's the space of transformation of S4 that preserves the orientation and angles are the group of conformal maps to the fourth sphere. Okay. Now, this, when I put it in red, means that it's just a boring calculation, but it's still a calculation that takes time. So, how to prove that are conformal? Is because remember that what exercise we did in Alfors, or in any book on complex analysis, is prove that any Möbius transformation is the composition of inversions, homothetic transformation, and translations. Exactly the same thing happens here. And here you have the definition of translation, quaternionic translation, inversion. Notice here is different, the inversion. No? The inversion is Q goes to Q minus 1. Okay? And then you have I'm missing one. Homothetic, this map. This map is interesting because you see, you multiply on the left by a quaternion C, and that means you dilate by the norm of C, and you rotate in SO3 by Q. And so any transformation, a composition like that, small computation, but it's an exercise, easy. And you see all these transformation preserves angles and preserve orientation. And this proves that indeed this group is a set of conformal transformation. Now, any conformal transformation by our elementary geometry class is a composition of inversions on spheres of different radii. Where a sphere is the natural definition, you take S4 in, because what's a sphere? You take S4 in R5 and you slice it with a hyperplane. And that's my definition of a sphere. And then you can always move to the equator. Inversion is change the last coordinate, and then by conjugation that defines inversion. And so exercise in elementary geometry shows that every Möbius transformation is a composition or reflection on spheres. And now, by our geometry course again, the inversion of the sphere on S4, you can take a sphere for dimensional sphere that meets the fourth sphere orthogonally, and you take R5 inversion of this sphere and restrict to that. I say that because this Poincaré shows that this group of conformal transformations of the fourth sphere extends as isometries of the hyperbolic space of dimension 5. So it's exactly like, I mean, I feel like I wish I had taken the lessons from Thorsten, but I imagine Thorsten explaining this in a really beautiful way, not like I'm explaining, but this is the way, no? So, so you take the set of Möbius transformations on the compositions, and this is what you see. So you go, remember that you go from PSL to C, from SL to C to PSL to C, divided by the identity minus the identity, group of order 2. Here's a little different. You have to divide by the center, which is one parameter, T times the identity. So let's think this is 16-dimensional, real. Divide by 1 is 15. And that's not surprising because the set of isometries of hyperbolic space of dimension 5 is exactly 15. Because an isometry is determined by fixing a repair frame, orthogonal frame at the origin, and see where it goes, no? So it means that is hyperbolic space itself, dimension 5, is the translation, plus SO5, and so it's 4. SO5 has dimension 10, 5 plus 10 is 15, so it's correct. So here with that, so you have that, and then the thing in red, calculation, these conformal maps, these isometries. By the way, when I say high school, I mean Russia, because now we don't learn that. I did learn with my professors old inversive geometry, but now that's not, they don't learn that. Okay, so have that. Now, mimicking the construction of the hyperbolic plane as the set of complex numbers with real part, with imaginary part positive. Now, unities I, J, K, it's better to think about the hyperbolic half space of dimension 4 as a set of quaternions whose real part is positive. So we just twisted, no? It's much better in this context to think of the hyperbolic space in dimension 4, to say the half space of dimension 4, which is the quaternions having trace, positive trace, having the real part positive, no? So this is a half plane. And of course, we give this half plane the Poincaré metric. And now consider, remember, going from PSL to C to PSL to R. PSL to R is precisely the subgroup of Möbius transformations that preserve the upper half plane. And now here will be a little more complicated because these are quaternions, don't commute, and the equality. So now you consider the set of transformations that preserve this plane is the analog of PSR. And this will be the set of isometries of hyperbolic space of dimension 4. So anytime I obtain a discrete group of that, co-compact, I give you an example of a 4-dimensional orbifold or manifold, and it will be beautiful. Maybe I can get something like Enrique, no? Maybe I won't do that, but maybe the Borromean links. But now, it's not the complements of knots, are the complements of tori or Klein bottles, because the ends are solved manifolds. So anyhow, this is just a repetition of what I told you. You have explicit formulas of that. And now, how do you determine the Möbius, the quaternionic Möbius transformations that preserves the half space or quaternions of real part positive? And this is beautiful. This was actually developed by formula by Alfors, all formula by Alfors, and by Wallen, a German mathematician whose history I don't want to talk about. And the condition is this, very simple. A Möbius transformation preserves this 4-dimensional hyperbolic space. It satisfies this problem. Here bar is quaternionic conjugation, and T is the transpose. And here you have therefore 4 conditions. It can be replaced by these boring conditions. Are equivalent. The 3 conditions are equivalent. The easiest one is the upper, no? The matrices that have this sort of conjugation. So the set of all matrices like that, and this is the condition. So you write A, B, C, D, and then you take the conjugate, and you take the transpose, you multiply, and you have 4 conditions like that. Equate coefficients of the matrix on the right and on the left, and that's. No, I don't understand your question. There's a mistake? This gamma is ABC. This matrix has the property. This is the first line. A matrix gamma A, B, C, D preserves the half space if it has this property. It's easy. This matrix times the matrix inversion times the other matrix square is equal to that. Eh? Is the same one? This one the same? See, these are equivalent. You can do it by hand, coefficient. The same in these 3 conditions are equivalent. Exactly. The easiest one. Yeah. I use the first one always. I use the first condition always. No entiendo, ¿cómo? A matrix A, B, C, D preserves the half space if and only if it satisfies one of these equivalent conditions. That's the statement. Exactly. Exactly. What? Yeah. I don't entiendo, okay? What? I don't understand the mistake. ¿Cuál es el error? What's my mistake? Where is my mistake? Yeah. I'm sure I made a mistake, so worry. Exactly. Exactly. The condition in the complex case is A, B, C, and D are real. PSL2R. Well, this condition is equivalent to that. But because we're...
That's notation. That notation is not any effort.
Uh-huh.
I want to know the concept.
The concept is when a matrix like that preserves the pure quaternions. You see, when and the sign of the real part. That's what it means, no? That's what. How do you discover? I mean, by the exercise for students, how do you say in 1 second that PSL2R is that what you want? It's because presents cross ratio, and the cross ratio is real, so it presents the real line, and then a small thing says presents the upper and the lower planes. This is the equivalent, but now you have to work harder because those things don't commute. But that is.
So this group is the analog of PSL2R.
See. And you will see this new, with this restriction, this manifold, we have the dimension 10. And that's beautiful because that's exactly the dimension of hyperbolic motions in dimension 4. Okay, so let's continue. Uh-huh.
These conditions prove you also the topology, right? You want to know what is the topology
Of the group?
of the group.
Yeah, I would say this is the next step. This is the answer of the topology of the group. You can do it in several ways. Since it's the group of isometries of hyperbolic for space, it will be hyperbolic times space times the space of frames of dimension 4. So it will be H4 times SO4. Or SO4 has dimension 6, 6 plus 4 is 10. And so that's precisely. And
The same as the group that has
exactly.
S4
Exactly.
is exactly like RP.
Exactly. And I will answer your question in a different way by proving concretely the Wasawa decomposition. And that's beautiful because you have A, B, C, D satisfying the BG conditions. I didn't know that Alphors had made it before, so I should have paid the Alphor conditions for mea culpa, no? Alphors did many things before, but anyhow, in this the last papers I corrected that. So canonically you gave me A, B, C, D, and I gave you a positive real number lambda, an imaginary number omega, and a matrix in SO4 like that. This is the Wasawa decomposition. It's beautiful because now I answer your question. The topology is SO4 cross for precisely, no, precisely what you asked. But now, okay, so here, forget about it. Those are what I told you. Given ABC, you can explicitly compute the orthogonal matrix and the etc. Now, because I want to do this, I want to obtain discrete groups of PSL2H, and maybe won't be discrete in PCL2H, but in PCL2H cross PCL2, no, sorry, in H4, let me call H, so, calligraphy, H, Hamilton 1, this 4-dimensional hyperbolic space. You see, we had a problem with writing this paper because it was Hamilton, hyperbolic. They were five H's at the same time, and so that was the most difficult part of the paper. But finally, we decided it's the best notation. H, calligraphic H for hyperbolic, index, wish field, and the dimension. So this is a 4-dimensional half space. Is a set of quaternions with positive real parts. Okay, so now I go back to this. Now you give me a quaternion algebras. So first I have to define what's a totally definite quaternion algebra, because I want to do things that are modeled on Hamilton, other things. I mean, well, anyhow, Shimura uses this. This quaternion algebra is one of the most beautiful things ever. And there's a free book that you can uncharge without being punished on the internet by John Voigt. Beautiful. That I recommend you to unload it. So let K be a number field. So a finite extension of Q, and Ck denotes its ring of integers. For example, we mostly take K equal Q, then Ck is simply Z. I mean, the ring of integers of the rational is the standard integers. And then if K is a quadratic field, then depends on the residual form, are of the form Z, C plus C theta, where theta is either, as I told you, in the case of 2, 1/2 of that. So this is the ring of integers. Observe that this is a ring of the reals, which is not discrete by Kronecker theorem. No, it's dense on the real line. Well, an order on a quaternion algebra over a field K is a four-dimensional ZK lattice that is also closed under multiplication. It's a ring, and well, it's maximal if it's maximal in theoretical sense. And yeah, I just want to point out that just one see that if Ck is a four-dimensional Ck lattice, means as an integer lattice of dimension 8. Like here, you see? This is isomorphic to Z plus Z, additive group embedded in the real lines. And so here this is dimension 8, and that's the reason I will have to do a Galois twist to have, how do you call to have discreteness, no? So you have that. Well, here I say that they are different. Here, contrary to the usual case, sometimes they are not maximals. It's interesting because here, units, multiplication by units twist your thing. No? So these are examples of non-maximality due to the existence of these Platonic solids. Maybe it's related to the work of Santiago. No, this is related to the Platonic solids in some way. Vignera, Marie-France Vignera has, I pronounce it bad, but you know. So, well, one of the most, so let me see, I started this work by taking, what happens if I take A, B, C, D, such that A, B, C, and D are quaternions, such that all, 5 minutes? I just started. Okay, so anyhow, I can actually, you know, I was 7 years in Italy, Mexican, I can use my hands. Okay, so what I'm going to do in this paper is construction of discrete groups. So one canonical example is matrices with Lipschitz integers. Lipschitz integer is a quaternion that has all the entries integers. N1 plus N2i plus N3i plus N4k. That forms a group, discrete group, okay? And it's a group acting on S4, it doesn't, on H5, and this is the determinant I told you, repetition, forget about this, formula only. And the point is that you take matrices with entries in an order, then these groups are candidate for acting, okay? And it's a priori non-trivial. It's an easy exercise. You see 2 lines, proving that if you restrict the elements of your matrix to an order, it's closed under multiplication. Could have been false, no? But it's true by a small calculation, but which you have to do just to be sure. And this brings you to the idea of the quaternion. Now, Hurwitz, one of my heroes of mathematics, because every time I learn more about Hurwitz, Adolf Hurwitz, say another important ring of quaternions, saying the quaternions such that all coefficients are integers, or all are half integers. Mix is not allowed. No? Todos hijos o todos centenados. No? All integers or all half integers. And that's marvelously, that's close under multiplication, and that will be the, now we have 2. We have PSL to Z, Hurwitz, and PSL to Lipschitz. And Lipschitz invented this to prove that every integer is the sum of 4 squares. Has an arithmetic meaning. No? Now I cannot do that. This is a schematic picture in 3 dimensions, but in the half space, remember the floor is pure imaginary quaternions. All the quaternions with real part positive, and then the fundamental group of the Lipschitz is exactly analogous. No? You have a chimney, and this is the fundamental domain. And then when you take the quotient, that beautiful object like that becomes another beautiful object. And then this is what I told you. But Hurwitz, I mean, Lipschitz quaternions are 1 minus 1, I minus I, j minus j. And Hurwitz quaternions are 24 of them. They all lie in the unit sphere. If you use the Cayley transform to send the upper half plane to the ball, and then you have 24 points, which is an absolutely gorgeous, has a Greek name as ikosasikososahedro, I don't know how, it sounds Greek to me, has a name, no? Object. It's called the 24 cell. How? What? The 24 cell, you take the convex envelope of that, and you say, it's exactly what John Parker says, that 24 cell has 24 regular octahedra. You know exactly the combinatorial properties. And then, if you glue in certain way opposite faces, you get hyperbolic form manifolds. In particular, for instance, you get in R4 there is 5 Klein bottles, so that you remove them from hyperbolic space, you have hyperbolic manifold. Reminds me of Thorson, no? Now there's no Thorson theorem, it's more complicated, but you have beautiful examples of. But anyhow, here is a new ingredient, there are units, and anyhow, this is the explicit formula how to extend from a conformal map from the sphere to the interior by explicit formula by Poincaré. It's called Poincaré extension. ¿Ya? ¿Ya? ¿A 2 minutos? ¿120 segundos o Mexican seconds or German seconds? Okay. Well, okay, so anyhow, let me tell you that if you take, I end up with this. I'm going to go very fast. Okay, so now take H. I finish with this. H, 2 copies of H. Sorry. 2 copies of that. And proceed like Blumenthal Hilbert. So now you have matrices, quaternary matrices, with entries are like Zk plus Zki plus Zk, integers of the quadratic field times 1, integers of the quadratic integers times I, times j, times k. This is a lattice of dimension 8. And then you have Galois twist. You add here, and now you have proved that you have a compact 8-dimensional orbifold. And the beautiful thing is that the ends are solved manifolds of dimension 7, which are suspension of a nose of diffeomorphism of dimension 6. And one challenging that I think is a project for students, the singularities a la Hirzebruch in the real domain, and see what happens. 8. 7. Yeah, it's a cusp. A cusp is caused by a solved manifold of dimension 7. It's the suspension of a torus, a nosov of dimension 6. Exactly. And this you can see by the and it's well, since I didn't have the time, I recommend you to read my papers. You probably won't, but it doesn't matter. The matrices are also 6 by 6. It contains beautiful arithmetic. Next but not least with my students, Elena, with Elena and Adrian Centeno, we're proving Sagier-Sarnak I claim, and the fault, who is at fault for working on this is sitting there. It's Dennis Sullivan who showed me that the Riemann hypothesis is a consequence of ergodic properties of whole cycle foliations. Exactly. And anyhow, we're working on that, which is the work of Venkatesh, of Hilinder Strauss. That's beautiful. Anyhow, this is just the beginning, and we already have about 7 pages. We have constructed non-commuted Aitchison series a la Saguier, and we are very happy that we are making progress on that. And this is the things that you won't read, but that you have put on the blackboard. But I'm very happy with this project because I'm dyslexic, and so every time all the mistakes in my mathematical life are due to non-commutativity and the Moebius band, the Moira phenomena, you know, coming with the wrong arrow, all my mistakes, you know. My thesis has a mistake because 1 for dimension 3. No, it's not full of mistakes. Anyhow, these are the Hirzebruch. Anyhow, finally, here is a and I recommend you to take from the internet John Voigt quaternion algebras free. Springer Verlag. Anyhow, we have at the University of Mexico, we have the right to take it for free legally. It's a beautiful book, which I thanks to Joe Quinn, I learned about this beautiful book. And anyhow, this is work in progress and things that are already been published. So thank you very much for your attention. Sorry for the.
Okay. Thank you very much, Alberto. There are some questions.
Because Laura Chass is studying Alicia Bull, she actually independently figured out the 4-dimensional Platonic solids. And we know the 5 Platonic solids in dimension 3, and there's one extra one in dimension 4. There's 5 corresponding to our 5, and there's one new one. I've always wondered about it. Then the 6, 2 are self-dual, and then they're in 2 dual pairs. That's the 6. And the mysterious one is your 24 self.
24, exactly.
Yeah, so this is sort of explaining
Exactly.
this new thing. And then above 4, there's only 3 in every dimension. So it's very special.
Exactly. You may think of simplexes and things that pretend you are learning, you are in the first class of Thorson, gluing tetrahedra. And here you know also, you know, I'm beginning to get emotional. That happens when you exceed a certain age, which is multiple of 4. I'm 20. Okay. Okay. Thank you very much.
Okay, one more question. Okay.
So in the Hilbert-Blumenthal case, classically, there's a correspondence between the cusps and the class group. So in this case, I guess you're working with these Lipschitz integers?
It's a very good question because the number of cusps in this non-commutative case does not equal the class
Is there
number.
even a finite class group for your...
But for this quaternionic, the class number is not the number of cusps. There's a little problem there. I think maybe by 1/2 or something. But it's a very interesting question. You have the same question you have, because you see how arithmetic enters here, no? Very deeply. And because PSL2H has so many subgroups, like for instance, well, with this I finish. So, 2 copies of H4. I did do it with my hands. 2 copies of H4. These are pure quaternions. H4, H4. Pure imaginary, positive real part. And then take the foliation as follows. What I mean, move your hand on a whole cycle at height y1 and the other at height y2. Okay? So it depends on 2 real parameters, y1, y2, 2 heights. And the group lambda minus 1, 0, w, satisfying the BG conditions, the one you were asking, preserves both, permutes, shuffles the deck of cards, and that's what gives rise to these solved manifolds. So 3 times 3, 3 plus 3, sorry, is 6. So every time you have something with real parts, y1, these are permuting, no? And so you have fantastic, what I want to say, fantastic holocyclic foliations and dynamics and ergodicity and radness phenomena. It's a really beautiful subject. Okay.
Thank you very much again, Alberto. The next conference is in 9 minutes, okay?
Okay.
Today, just before the lunch, it will be the poster session. Not everybody got the opportunity to give a talk, so previous to the lunch, it's going to be the poster session. So please take a look.
O lo que quieres tú lo puedes prender en la sala. ¿No las cortes?
No. Vamos a probar. Ok. para salir de esto. Luego se fueron a las escenas. ¿Cómo? A ver qué tal sale. ¿Se supone?
Mientras si quieres.
A ver,
Aquí sí sabes, ¿no? Aquí,
No.
aquí tiene un botoncito.
Okay, come in. We will be start. Please sit down. Okay. Okay, the next speaker is Professor Valdemar Barrera Vargas from the University of Yucatan, and he will talk about counting the connected components of the discontinuous region in the certain families of complex Kleinian group. Please, Valdemar.
Many thanks to organizing committee for his invitation for celebrate the anniversary of Pepe Seade. I will explain a problem, the content components of discontinuous relation of certain families of complex Kenyan group. I don't have and really solving this problem. But I will tell a story about how some progress about this problem. I will give a brief motivation about the classical Kleinian group, some important result about classical Kleinian groups, a summary about complex Kleinian group, what means a complex Kleinian group, a summary of the main results about complex Kleinian group, the complex projective plane, and finally the statement is the problem of what means to count the component, what means some advances we can do. So, firstly, probably I don't sure about that. But in 1983, Poincaré introduced the concept of Kleinian group. The Kleinian group are precisely the most easy version is called Mobius transformation. But also we can think so CP1, group of the complex projective plane, or also homotic positive. And an important thing in the Kleinian group is the limit set. I introduced the definition as a limit point. It's precisely when you choose a Mobius transformation in this way, you put limits and you regard what happened in this Riemann sphere. And you put all the limit set in a set. That is called the limit set. If we denote the limit set precisely by gain. Also, the limit are the parabolic is precisely in the transformation that have this normal translation. The loxodromic element is precisely this kind of the transformation when the modulus is different one. I wish a picture about limit set. I take this picture from internet. This is an amazing picture for attention when I see probably the first picture of ASCOP and limit set, because is an unknown student or freak to this picture. I will show probably we begin with this configuration. After some inversion, you repeat. You obtain something like that. At the end, you continue, and you obtain something like that. At the end, you obtain a beautiful or that is a French mathematician that I take a picture of the webpage. And another in the pair, beautiful, so beautiful. So the limit is a mathematical object, very beautiful, dynamic. But what happened with property? Principally are to follow. We said two are called elementary. In the contrary case are called no elementary. The most interesting are obviously lost the non-elementary because the dynamic is very. So you have an limit with at least 3 points. The gamma orbital is dense into limit set is closest set and gamma in the game so any is a cumulative limit set. The limit set not in Soleil point. Here the gamma zero 10 and the complementary of the limit into sphere. The discontinuity relation has is when omega gamma is not empty. It has 1, 2, or infinitely many components. That is the start of the classical theory of Kleinian group. And I will try to give the precisely in this point in the context of complex Kleinian group. Kleinian group that is well known. The complex Kleinian group have immediately. Another is we have only topology, only contact geometry, but not have the full tool or speaking formal geometry. So that is the beginning. The beginnings are 2 seminal articles of José Seade and Alberto Berkowski several years ago. The definition is very simple, and gamma is a subgroup of piezo electricity acting in the complex projective plane. We say gamma is a complex Kleinian group. It exists a non-empty optimum set. So the following, which invariant on the action of gamma. Gamma act properly and discontinually on it. It's on this definition. And Alan, when given a gamma group of piezo electricity, how can we define a complex Kleinian group? That is a hard question, normally. Pepe Seade, together with his student, the doctoral student Juan Pablo Navarrete and Ángel Cano, gives a lot of progress about this subject. He went in and he published this beautiful book. This was the start for me for introduce me to this theory. Now, in this part of this talk, I will introduce some evidences, some with Ángel Cano, René García, Juan Pablo Navarrete, and José Seade about this subject. First, we have a classification about the atom of CPN according to that or about the PU1E. Now, to come, they this classification, gamma is elliptical, is enlightened easily 1C, which is diagonal with unitary motion values, is parabolic, is a leaping itself in CC, which is diagonalizable with unitary values. It's loxodromic, it has a life in plus at least one eigenvalue had not modulus 1. So task classification is very good, but classification according to a limit set. The limit set is, the principal tool is Carney limit set to describe the dynamics of this kind of limit set has three pairs, L0, L1, and L2. The L0 gamma is the closure of the set of point 1 with infinite isotropy. After removing to X L0, we take P and U accumulation point of this orbit. After that, move L0, L1, and you repeat with the accumulation point of the gamed orbitals compact set in this set. That's the complementary of this space is called the this group. In 1972, Kulkarni showed this in very general journal for topological space, Hausdorff space, locally compact, group of the homomorphism with compact open topology, and he showed L0, L1, L2, and Langley gamma are closer than game invariant. The action in the complementary is proper and discontinuous. It's not empty. Yeah, and another thing, by example, the exact countable basis for this topology game is the client is the same. Game is this theorem in the context of the setting, especially Huasi, we say this set, the discontinuity region is not empty, then gamma is a complex claim. But if you remember, Alberto Seade, we don't have a way to find and discontinuity region. So the Kulkarni tool give a way to discontinuity. So according to this tool, we can describe the dynamic, the element with the Kulkarni limit set. For example, parabolic is an only if the limit set, the Kulkarni limit set consists in single projective space proper. Its Loxodom set consists exactly two disjoint projective space which have and wall CPN. When he make where to precisely this line E1, E2 in CP2 as precisely when Kulkarni set is E3. Element, actually, this representation when E1, E2, E1, E3. In one of these lines is acting a parabolic element, in the other, if finally the strong logarithmic element when the eigenvalue precisely with this relation, strict relation. So, in each of these lines, the transformation act with a logarithmic element. This story of this result about the complex Gaussian loop electricity current limitation is bigger than the classical Gaussian loop. One, three, that is como similar to first result about the elementary or no elementary. And concept, what into how many these lines are in general position. It's a mistake. Yeah. Exactly. That is this. Exactly. Yeah. Thank you. Thank you. But by some two line in the project plan. How many? But so, every except the number 1, 2, 3, or if I will talk on the next. An example. Yeah. Yeah. All right. For everybody. In number 5, use the limit set of cyclic group generated by logarithmic element. Here is a mistake, so that gamma 0, finity, then cyclical limit set. Finally, if the number of linear in general position at least invariant line or global fixed point, then lambda current limit set is complex line. It's similar a Kant. So, my purpose is explain now. I will give some examples. We studied the complex hyperbolic geometry. You have and discrete subgroup, co-compact discrete subgroup in this geometry, you have only one component. A limit set precisely this set is P2C minus lambda cool, lambda critical current limit set. So when you have a co-compact action in this geometry, set is precisely at the upside of the unity ball. So only one question. Another is when you have two components, is precise a suspension element as is projective is precisely at open four-dimensional ball. When the complex con is one. Example, Pepe Cano Park. Component. Coordinate. It is of line. Complete to 3 open 4. Example. And computate the number component are precisely in a union of four components of this kind of space H times this. So we have a conscious truth, probably it's true. The Kulkarni region has 1, 2, 3, 4 infinity connect components. Yeah, sir. Yeah. That is possible to, when you have lattice here on the solid manifold, that is co-compact. It's a solid manifold, lattice and solid manifold. It's co-compact. It's possible to show that. Now, representation of modular groups to do a Gusset and Parker. That is a representation. We have several 30 and set of is representation when you have and see the representation of modular group. By example, when A0 we have and C fusion representation. You have only two components in the region of discontinuity. When this part when I air refusion we have 3 components. You have or still limit set. You can watch there are a long forward. I think probably this example I infinity many but I will give, we don't have to substitute to prove that. I will give some evidences about this problem. But so we can consider this construction. You consider H3, the boundary of symbolic space. We can estimate the first component of this set, motivated by the theory of we can this problem with an space is called change space. The change space is you choose a complex line to intersect with each that give a circle and visual of change. Do the follow. You imagine, can you something like that? That is a point. That is a chain. In section, you can deposit the vector with the chain. You can change you can change a chain with a positive vector. We have a polar identification. We have a topology. But or compute for estimate the number of I was directly to resolve estimate the number of component in the complement. We can compute the link number in the chain. So their points are in different components. So the number of different linking that we obtain is probably or different components in this set. This picture probably is capable to find family of chains with the linking number increase arbitrarily big. We have an infinity component, probably. It's only an idea. We don't have success yet, but we have some progress. By example, we can in the previous we can we have 0 or 1. So the number of components is almost 2. Yeah, precisely 2. When in the sample of space we can also compute the number, the linking number, 0, 1, minus 1 component. With this kind of algebraic curve, we can compute the number component. In this case, because n is bigger than image, we have one component. Computing the linking number. We can also describe this set. We disjoint or and finally, well, thank you for your attention. Happy birthday.
Okay. Thank you, Waldemar. There is any question?
So in the examples you construct, can you actually see what at least one of the components is?
One component.
What can you? I guess what I'm wondering is, can you compute the stabilizer of a component? If you can identify a component and compute the stabilizer,
I don't
or
know.
the set of transformations that preserves the component.
We don't have a final number, yes, but we don't have, well, now we don't have an example, infinity number. I don't know, it's preserver or change. No?
I mean, but can you sort of say in a specific example what one of the components looks like, or is that?
Change of the component in one and another.
Okay.
No.
Can you give a description of one component in one example? Geometric description of one component.
By example, it's possible. By example, the Gaussian space or something like that. It's possible, by example, here. No, it's not. Here is possible. That is
Mm-hmm.
Is it the complement?
How to say? In the case of this kind of partial, which you can do explicitly, but symmetry or zero is the action. But we don't have an algorithm that all the time. That's complicated. Yeah.
Concepts relate when you go to the dual action.
When we go to dual action, it's a good question. I understand a little. And concept of what or the concept Gibbard limit set. This concept Gibbard you consider the action in the dual space. The union of the projected space will recuperate the current limit set. That is possible to do. It's a work with Adriana several years ago, Adriana Pablo.
Okay. Only one question more.
When you have infinitely many components, can you have
It's a question. Huh? I don't know. Yeah. Infinitely many components, infinitely many orbits in the complex.
Okay. Thank you very much, Waldemar. Okay, the next conference is in 5 minutes. 5 minutes, yeah.
te dejas intimidar. Porque pinche Valdemar, todas las preguntas que hacían las podía contestar, pero se asustó y no contestaba nada. ¿Estás de acuerdo?
No llegué, no
Ah, no
llegué, estaba yo
llegaste.
corriendo. Voy a hacer lo posible. Espero que te guste, pero no.
Estoy seguro que sí. No, y está muy bien eso que estás hablando, está muy chingón.
Ya no te lo envié, pero como
Vale,
tengo un
vale.
corrector de esto.
Hola, hola. Kevin, will we start, please? Where is... Sí, ya vi. Okay. Okay, the next speaker is Professor Ángel Cano, and he will be speak about the representation variety of nodes. Okay? Please, Ángel.
Before I start, I want to say a few words for Pepe. Pepe, thank you very much for all the support and patience during the last months. I really appreciate it. Enjoy your topic. You are a really nice project. Okay. And so, this talk is going to be about the representation variety of nodes. Essentially, this go for in time, a long time ago, when I was a student, and I heard the previous talks with Alberto and Pepe Seade about nodes, and its functions into cleaning groups theory. So let me talk you what we were doing as a group, because this job is joined with Pepe. There are a lot of years of Alberto, my students, Patido, and so on, right? ¿Se murió? If it can happen, happens. Yeah. So in this talk is divided into 3 steps: introduction, logs and links, and a new structure, at least for me, which is called quandles. Okay. So let's start with a little bit motivation. This motivation, as I told you, comes from questions that Pepe and Alberto asked me, and also I think Juan Pablo and Valdemar, a long time ago when I was young. So the first thing is that is central for our group is what about the Sullivan dictionary in high dimensions. The second is to Sullivan finite theorem into other lists. And we started to slow down the question because the first 2 are very hard to ask or say something, at least for me. And started with a more naive question, also for Pepe and Alberto. The question is what happened with the counterexample of Misha Kapovich and Leonid Potiagalo for the Sullivan finiteness theorem into hard dimensions. Because the Sullivan finiteness theorem asserts that if you had a finitely generated group of Mobius transformations, then there are finitely many conjugated classes of maximal parabolic groups. Right? So around the 80s of the past century, Misha Kapovich and Leonid Potiagalo give a fantastic counterexample that asserts that in high dimensions, in the case of conformal group of Mobius transformations, finiteness Sullivan theorem is not longer true. Okay. So if you are trying to understand what happened with this very beautiful theorem of Professor Sullivan, the space where it's simple, the space where the problem looks in the simplest is the case of biolomorphism of the unitary body. Okay? So what happened in this case, right? So if you give this fast lecture of this counterexample of Kapovich and Potiagalo, the original one, because later the guys have, I don't know, 4 or 5 papers about it with improvements. In the original paper, you can show, or it's possible to see, that the two main ingredients of the counterexample consist of, first, the Borromean rings admits a complete reality structure. I'm going to show you a picture of the Borromean rings, and I'm going to tell you what they mean. And also the other main and key ingredient of this construction is the use in a very heavy way of the Poincaré polynomial. I want to say that, and this I learned from Professor John Parker, that Poincaré polynomial theorem is very nice theorem, but this is a theorem write down and speak about it with a lot of patience and having a lot of warnings, because paper of Petronio, you can show that most of the known right and statements of the Poincaré polynomial theorem are false. So you proceed with a lot of caution. Sorry. If you want to say something about this theorem and try to understand what happened, if you can reproduce this Proteagallo reconstruction, you should do something like this. Right? So the Borromean rings is kind of linked. So you have 3 circles, and they are put in a way that if you could one, the other ones are not. Okay? And this thing that are beta complete hyperbolic structures, it simply means that its complements can be uniformed through a group of 3-dimensional real hyperbolic space. Right? So, by the way, this part was done by Thorsten in I don't know, in a lecture. You can find a place, no? And I'm going to talk about this in a more detail. So, what kind of problems do you find if you're trying to follow this path? The first thing is very difficult to compute representation of knot groups. For example, there is a very nice paper of Elisha Falvel where he tried to extend the method of Professor Thorsten, in this case of generally groups, etc. The main problem is that in his case, when you confront the number of when you confront the system of polynomial equations, the number of polynomials that appears grows exponentially. Okay, so in terms of the computer, this makes the problem very difficult. And also, it has another problem. The problem is that when you look at the Falber, is that it can happen that the system of a polynomial equation that Falbers will give you, the system cannot have solution. Well, the idea or the obstruction behind these problems or these difficulties is that in the case of Falber is interested not only into computation, he is also interested in solving the problem where a 3-manifold admits a CR structure, whatever this means. Okay? So we have a problem here. And another problem that I learned from John is that it's very difficult to have a complete version in the case of PU21. This is working problem. The only person in the world that knows about a lot of this, I think there are a lot of people here, but the expert is here, and well, we are expecting your version. Okay. A lot of people. So we have 2 main problems here. Well, let's see what we can do. So let's return to the basics, right? Consider diagonal complement. I have a picture, and in the 1972, something like this, Riley proposed or give a representation of the fundamental group of the egg-node complement into the set of into the group of Monfils transformations, right? And if you read the paper, it's very nice. And essentially, what he does is he considers the group. It has a representation. It has two generators, and the generator satisfies this relation. Right? So later he said, well, let's take one matrix and let us assume that one of the generators is going to be sent to this parabolic element, and the other one is going to be sent to another one. Right? He's considering that the generators are evaluated into a parabolic transformation. Okay? And if you put these matrices and you ask these relations must be preserved, then it's very simple to determine that the system of OK is this one. And as you can see, it's a very simple system. Okay? So if you proceed the way I did when I was younger, you try the same thing. You put generator, which is an upper triangular matrix, and you put another one. And you try and you put in the computer, and you look what do you get. And most simple or stable equation that you get in the system is this one. And this is, so let's see if we can do this. So just for mental peace, for my anode is, when you think about anode, is going to be an immersion of a circle into S3, and we are going to think that they are same. I mean that you, when I told you think about things that appear in this table, right? I don't want to, and I don't have time to say more. The things that we are avoiding as avoiding is not of this kind. These are very difficult objects to deal with. Some language, if you have a node which can be projected to a plane, or if not a node, you can deform it through an isotopy in a way that you can assert that this node can be projected to a plane that looks this way. Yes, this projection is the diagram. Okay, and in this case we are projecting at the point. These are going to be called the crosses, and these are the paths that we are going to generate the group. We are going to see later. Rademaster a long time ago showed that if you have a diagram, then you have three moves that solves all the life. You have the first type move that simply if you have this kind of thing, you can put strike. You have this one, you can separate, and you have the other one, right? Which essentially said that you are doing nothing to that. So the impressive theorem of Rademaster is that if you have two links, they are equivalent in the way that the other one, and only if they can be connected second Rademaster move. Right? As you can learn from Alberto, Fico, and Mario, this can be a very, very difficult problem. For example, if you consider this so-called Culprit-Kaufman knot, if you saw it, this one at the first sight, you cannot say that this is the trivial one, but after a very, very clever Rademaster move, you are going to see that this knot is trivial. So it's not a very simple, it's a very difficult problem, right? I don't want to say more, please. Well, I want to talk about a structure, that an algebraic structure that was introduced by Joyce around the 80s. For sure, Joyce was not the only guy who introduced this structure. Arnold was thinking about these kind of things at the same time. You have also the group of mathematicians in Japan. There are a lot of the Russian group of mathematicians also were working in this kind of ideas, right? So this is a structure which is not associative, and if you are working with groups, as I am working, when you saw a first, you are going to get afraid. But as you can see, as we are going to see, this structure which is pretty nice. The main aim of this definition is simply to codify the notion of Rademaster moves in an algebraic language. So it can be think as a way to put all the information of the node, all the important information in the node, in a structure which is very compact, right? So we have three three items that should satisfy it. The first one is the operation is idempotent. The other one is that whenever you consider this kind of equations, you can solve it, okay? And the last one is that you have this very strange kind of associativity. If you go from dynamical systems, you can show that this is simply the properties of conjugation, right? This one? This means that when you consider this function is one-to-one. Okay. Beta is that it simply means that to the element x, you are going to assign this element. That operator. Yeah. Thank you. So, as I told you, this notion or this strange structure simply codifies the Rayleigh-Master moves. For example, you can show here if you have the first Rayleigh-Master moves, it's simply the first system simply says that A operated with A is the same thing, right? The second item corresponds to the second movement. The third item corresponds to the third Rayleigh-Master move. As you can show, this structure is simply put in a very formal language the notion of Rayleigh-Master moves, which is really pretty nice because it is going to lower the difficulty of the problems when we are going to compute things. So let me give you two examples of quandles. The first one is, as I told you, the conjugation quandle. When you have a group, then you can make it a quandle simply by the conjugation, the quandle operation, the conjugation. So the conjugation is a very, very, very simple operation, and we are used to it, right? The second operation is more or less the same, and it was designed by Joyce and Matev, and you have a group and you have a subgroup. Then for each M in the center of the group, you can provide a structure of this quotient in this way, right? So you can make the computation, but these are examples for us. So we also have notion of the fundamental quandle. Given a node, can assign it to a quandle. As we did with the fundamental group to a node, we can assign a quandle to a node. And in fact, it's very simple to do this. You take a node, then you take a tubular neighborhood of it, and then you fix a point by this neighborhood, right? And then you consider all the paths from this fixed point to the boundary of this tubular neighborhood, okay? Then all the homotopy classes, this kind of paths, which is going to be called the fundamental quandle of the node. And now the thing is, how do you pair these things? It's the thing as we did with the fundamental group, right? It's very simple. You take one, you record the path, then you record a meridian, then you go back, and finally you record the other one. So it's the same thing that we did with the fundamental group. The idea is very simple, okay? As you can see, this is going to provide us a close relation between the fundamental group and the fundamental quandle. The information that codifies the fundamental quandle is more precise, but this also can be translated in several cases in a very good way to the fundamental group and the other way. For example, it is well known that the fundamental group is not a complete invariant because there are nodes which in fundamental group, but they are not. In the case of fundamental quandle, this is not true. If you have two nodes which have the same fundamental group, they are either the same or they are different or they differ by orientation. Okay? This term is true or not. In the case of links, it's not true. So it's a very nice thing. So it's not very difficult to prove, but it is going to be the center of our talk. Joyce, Matej, has realized that this is a very, very, very important item, and this says the following. it asserts that you compute representation of fundamental graph of the link into a group, the group that you want, is the same problem, or just that is the same problem that computing the set of homomorphisms, but now in the quandle category, right? From the fundamental quandle, but now in the conjugation quandle of the group. So if you want to compute things here, it's the same thing that you compute things here. Okay? The main thing the main aim of this talk is that show you that the problem of compute things here is more simple. It's not a panacea, but for sure it is going to slow down the difficulty of the problem.
You said what Q naught of a link is?
Sorry?
What is the quandle?
Sorry, I'm.
What is the quandle? Q naught of a link. Q naught.
The fundamental quandle. Okay. Is this thing? Thank you. Okay. So, how do you proceed to compute elements here? How do you compute arrows here? And it's funny because compute things here is like we did in our course of linear algebra, right? In linear algebra, you assign to each element of the device an element in the domain, and then you extend. Here you are set in the same way, but now you be careful. For each element of the fundamental quandle, you assign to image in the group that you are going to work with, and then you only need to ask an extra. You need to ask that all the images satisfy the same relations that the generator satisfies in the original one. It's a little bit natural. So if you get an arrow that satisfies these two things, you are going to ensure that this arrow is a morphism in the conjugation, in the quandle category. Sorry, I don't like it. So what do we do, or what are we doing to ensure that the problem is now more manageable? So the first thing that we observe is that the group endowed with this conjugation, you can study conjugation classes of elements, right? So we proceeded in the following way. You have a group, and then you only consider the orbits of conjugation elements, right? So the other thing is that each conjugation class of elements is simply the group quotient the commutation of the element, right? So this means that in a way, if you have the group, you can put this into an orbits, and the orbits are very simple objects. So the other thing is that these very simple objects admit the Joyce-Matthijs structure as a quandle, as I told you, right? In this case, the Joyce-Matthijs structure in these conjugation classes look in this way, the operation, which is very simple. When we saw at first this expression, one can think that this is going to provocate that the number of polynomials and the degree of the polynomials is going to grow very fast, because you at first have two multiplications of matrices, and then you have 1, 2, 3, 4. Okay? And it is expected, or one can expect, that the degree of the polynomials will grow. And surprisingly, the degree does not grow. In fact, the degree is slowed down. Let's talk about an example. This is a toy example. But if one understands this toy example, for sure we can do a lot of things, right? So recall the group G can be put, understand, as several orbits. You can see classes, and this means that you can write down the group in this way, okay? Where you are able to parameterize all of this under this relation, right? So using the Iwasawa distribution, which is a to parameterize the groups and in a very fancy way, we can say the following. We can say that all these leaves, yes, can be studied into three kinds of leaves. The first one corresponds to the parabolic element, right? You have the parabolic element and you have this deep ellipse, which is a very special one. The other, an idempotent element. You have an idempotent element, and then you consider it conjugacy class. This is going to be very, very, very important. The things that we need to say, in case of parabolic, the leaf of parabolic correspond to this guy, which is very simple. In the case of the idempotent element, leaves can be simply described as this guy, but you need to collapse a line on it. This is called a blow down. Sorry, I'm not expert in algebra. And in all cases, which are almost all the quandos are isomorphic as a quandos. Okay? And topologically, this quandol, can be described as this guy, but you blow up a point. Okay? So this gives you a precise, very nice way to understand the leaves of this composition. Also, as you can see, a very nice way to say that, to understand the representation variety, it says you how many systems of equations you need to solve. This says that you solve parabolic ones, you need one loxodromic, and once you resolve one loxodromic, you resolve all the other, and you solve idempotent case, right? So if you solve the loxodromic one, solutions have to put all these parameters. The other thing that you take care of is now you need to the parabolic representations and the idempotent representations. So you only solve, you are going to be able to determine the representation variety of the node. Okay? So as you can see, this tool is very, very simple, and if you sometimes have read the work of Pico, when you use the track of the topology of a very difficult problem, or not difficult problem, but the language is very complicated. And in this, we have that the quandles, the tool that specifies the language and make all theorems very easy to and very easy to understand. And we can go further. Well, this is what I told you. And as you can expect, all these results can be translated in easy way to another Lie groups, because the main result that is back, or is back. Sorry, the main result that supports all these things I am telling you was our decomposition terms. Right? So, well, you can recover. Sorry, I don't have enough time to do, but you can recover classical results. For example, you can give sharp estimation of the dimension of presentation variety, detect in a simple way singular and regular points of the representative variety, and also you give estimations, not very good, but good enough, of the number of the irreducible components of the representation variety. Okay? And well, we expect that we can do more, but we are still studying this kind of objects. Maybe in forthcoming papers with Pepe, we are going to be more. Sorry. To tell something so you can get the idea. Sorry, I'm not very good teacher. I'm very worth at explaining. Consider the following ways. Consider the A naught. Okay, it's not hard to show that in the case of the A naught, using the translation theorem in the case of the same way, now the commutators by expression, the fundamental quandle of the A naught has two generators and satisfies these two relations. Okay? So repeat the I told you that generator, you assign a matrix, and you force that the operation of the quantum of the matrix satisfies these relations, and you put into the code is the following one. As you can saw, is very natural. A, C, X, Y, A, and B. One second. This one, X, A, B, C. Ya se me acabó el tiempo. 5 minutos, 1 minuto. 1. You can compute. The main thing is, or the novel thing is that in this case the polynomials are ordinary and are what do you call are homogeneous, are mixed, which is new, at least for me. And so you can get a lot of using the computer. For example, we get the results of Albert, which asserts that the number of representations of the H naught complementing to PSL3 are exactly 6. And we have all these things. Okay, as you can see, the tool is very, very, very nice. You can program in the computer in a very simple way, and you get results very quickly. And to close and say no more, I want to make a special mention of the following result. This result is from my undergraduate study or student, Kevin Celis. Kevin over here. Kevin's over there. And Kevin, using this machinery, is able to show that the set of reducible representations of the programming rings of the fundamental group into U1 and set meridians into 3 omnipotent elements consist of exactly 4 things. I want to mention this because when I try, and my colleagues and my other students try to solve this problem using this machinery, we... ¿Puedes poner la otra diapositiva? We confront, sorry? Let me show you what Kevin did. ¿Se murió? Kevin confront the following system of polynomial equations. We tried with the computer of IMPA, we tried with the computer maybe Falbel, we tried with and we tried with the computer at the union, and all the computers, and in I don't know, maybe 5 pieces of paper was able to do this. How solved it by Kevin? In any case, these are able to have one of the main ingredients to the Potiagalo, know about the discreteness of the group. Until John gave us the version of the pointer. And that's all, Pepe. Feliz cumpleaños.
Okay, thank you very much. There is some question? No? Okay. Okay, thank you very much again. The next conference is at 12 o'clock, okay? In 10 minutes. 12, yes, yes. No. 12. In
Really great talk, well done. I learned so much in that. So.
Seriously?
Yeah, because I'd heard quantals, I'd never really know what they were useful for. And Kevin's results are really impressive.
Turn on? Turn on.
Testando. 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 Hello.
Hello? No.
Hello. No.
No, no sei.
Está.
Okay.
Ok. Gracias.
Con esto.
Mm. Good.
This one is okay. Before. Okay, you can. Now it is. Ahora está encendido. Okay.
Vou deixar.
Okay.
Gracias.
Okay, we'll continue. The next speaker is Thais Maria Dalbeló, that will be talking about of local Euler construction of isolated determinantal singularities. Please.
Thank you very much. Good morning, everyone. First, I would like to thank the organized committee for the opportunity of participating of this conference in honor to José Seade. Feliz aniversário, Pepe. Feliz cumpleaños. This talk is divided in these three parts. First, I'm going to talk about local Euler obstruction. After, I'm going to present the definition of determinant alvarite. And in the sequence, I'm going to talk about Newton polyhedra and some concepts related to this object. And so, using volumes, I'm going to present a formula to compute the local Euler obstruction of isolated determinant alvarites. Okay? So let me start. Well, the local Euler obstruction was the main ingredient used by Macpherson in his proof of the Deligne and Grothendieck conjecture, which deal with the existence of characteristic complex singular variety. Okay? And sometime after, Jean-Paul Brasselet and Marie-Hélène Schwarz, they gave they present an equivalent definition for this invariant, and this point of view brings the local Euler obstruction to the class of the index of a vector field. Okay? And although it is very important, the local Euler obstruction is difficult to compute. So, but many authors has been working in this subject, has been studying this invariant, and present formulas which help us to better understand this invariant. For instance, Le and Tessier, they present a very beautiful formula which says that the local Euler obstruction of a variety at origin is equal alternative sum of the polar multiplicities of this variety at the origin. Okay? Brasselet, Le, and Seade also presents another very beautiful formula, which is a kind of Lefschetz type formula. And this formula says that we can compute the local Euler obstruction using hyperplane sections. Okay? More recently, Gaffney, Grulha, and Ruas, they compute the local Euler obstruction of generic determinantal variety using the combinatory which lives in this kind of variety. Okay? In this presentation, in this work, I am going to use the formula given by Brasselet and Seade. So for me, in the presentation, I will use this formula as a kind of definition of local Euler obstruction because I don't have time to introduce all the ingredients to define it. Okay? So this is the formula presented by Brasselet and Seade. So let X be an equidimensional reduced complex analytic germ of dimension D, and V a Whitney stratification of X. Give a point P at X, the local Euler obstruction of X at P is equal to 1 if P is a smooth point of the variety. Otherwise, if P belongs to the singular set of the variety, then the local Euler obstruction of X at P is given by this formula, where here L is a generic linear formula with respect to x. B epsilon is a small ball centered. And here, this denotes the Euler characteristic of this section. And here, this is the notation for the local Euler obstruction of x at a point of this stratum. As the local Euler obstruction is constant along a stratum of a Whitney stratification, this notation is okay. So, a particular case of this formula is when x singularity. Let's say at the origin, for instance, okay? Then, in this case, we know that a possible Whitney stratification for x is this one with just two strata, okay? And this strata is the smooth part of the variety. So, in this case, the local Euler obstruction of x at 0 is equal to the Euler characteristic of this section, generic section, okay? Well, in this particular case, this formula, this equality, was also presented by Lentessier, Cato, and Dubson, okay? In this work, in this presentation, I am going to return to this equality, okay? So now, let me introduce the definition of determinant alpha right. So, consider M and K the set of the complex matrices of size n by k. And let us denote by M and Ks the set of matrices with rank less than S. Considering A holomorphic map germ from Cn to the space of matrix that I am going to denote in this way. Then let XAS be a germ of the variety defined as the preimage of MNKS by the map A. Then we say that this variety is a determinantal variety if its dimension is given by this expression, which is equivalent to say that its codimension is this product here, okay? So, as some example, hypersurfaces are determinantal varieties. Complete intersections are also determinantal varieties. But, of course, we have determinantal varieties, which are not hypersurfaces, neither complete intersection. For instance, if we consider this map here, given in this way, and if we consider the 2 by 2 minors of this matrix, then we have these 3 binomials here, and the zero set of this ideal is a surface in C4. But we can easily check that this product here is also 2. So dimension 2 in C4, it is a determinantal surface, okay? So now I'm going to talk about... Yes, it is a determinantal surface, okay? Well, let me denote by XA this monomial here, okay? Where A is a emupla of positive integers, okay? And let F be a polynomial function given in this way. Then the support of F is just the the M+, which appear here in F, okay? Then the Newton polyhedron of F is the convex hull of this union here, where here what we have is the Minkowski sum. So here what we are doing is at each point A in the support of F, we translate the first orthant of Rm to this point, okay? After we do the union and take the convex hull. This is the Newton polyhedron of a function. Here I have a very easy example, okay? So if F is this function here, then it is, we know that x to 3, in fact, is x to 3 times y to 0. So to this monomial, we associate this point, and y2 is equal x to 0, y2, and to this monomial, we keep this point, okay? So, oops. To this point, we need to do the Minkowski sum. Then we translate the first orthant to this point too. And after that, we need to take the convex hull, okay? Let me remark in this example that this function, the Newton polyhedron of this function, touch this x and also this x. We have coordinate x in this case, and the Newton polyhedron touch all the x's, okay? So this, if we remove from the first orthant of the Newton polyhedron, what we have here is a bounded polygon. So can compute the volume of this polygon. Okay? When a function satisfies this, when the Newton polyhedron of a function touch all the coordinate axes, we say that this function is a convenient function, okay? It's a convenient function, okay? So here we have the definition of Newton non-degeneracy condition for determinantal varieties, which is a generalization of this concept for the case of hypersurfaces and the complete intersection. And then let A be a germ of a holomorphic matrix, which defines a determinantal singularity XAS. We denote by delta J the Newton polyhedron of this entry of the matrix. And here, let me observe that delta J does not depend on I, okay? So the Newton polyhedron does not depend on the line. The matrix A is said to be Newton non-degenerated if for each collection of faces of this polyhedron, such that this sum is a bounded face of this polyhedron, then the polynomial matrix given by this restriction defines a non-singular determinantal variety in the algebraic torus. In this case, we say that this variety is Newton non-degenerated determinantal singularity, okay? Here I have an example. Okay, in this example we are going to do that, okay? So for instance, if we consider this matrix here, then we have 3 columns, 3 rows, first row, second, third, and here the then we have polyhedron, delta 1, delta 2, and delta 3. But in fact, they are all equal here, okay? The Newton polyhedron of this function is the same of this one, and it is the same of the last one. Then in this case, we have just one polyhedron, Okay? So, for instance, this polyhedron is the polyhedron generated by this support. The support of each entry is given by this set. I think it's 2. And the last one, I think it is 4. Okay? Okay, gracias. So, for instance, this point is a face of such of this polyhedron, right? The sum of these 3 polyhedron, in this sum, okay, we are going to have a face, a bounded face, which is given by this point. Okay, so if we sum this bounded face 3 times, then we're going to have a bounded face of this sum. And then we need to check if the restriction gives us, in this case, a determinantal variety without singularities at the algebraic torus. We need to do this for all possible combination of faces such that the sum is a bounded face here, okay? Even in this example, we have a lot of cases to test. It's not so easy to do this by hand. So we did this using the computer program Oscar. Then we did the computation, and we checked that this matrices is Newton non-degenerated. Okay? Now, here our first result that says that let xan be an isolated determinantal singularity defined by the map A. Okay? And let us suppose that the Newton polyhedra of each entry does not depend on the line, okay? Like in our definition, just depend of the row, okay? And that they are convenient. If the matrix A is Newton non-degenerated, then the local obstruction of this variety at 0 is given by this sum here. Where here what we have is just a binomial coefficient, and here what we have are mixed volumes of polyhedra which are associated. Okay? So the proof of this proposition, it was not difficult. It was, in fact, we will use this work, the work of Sterov. Here, he gave a formula to compute the local Euler characteristic of the Milnor fiber of a non-degenerated function defined in a non-degenerated determinantal variety. So we just apply this. We consider L a generic linear formula, and we just apply this formula, okay? It was easy, but we improve here. Our most contribution was improve here. In this way, it's easier to compute this kind of volume, okay? Well, for instance, if we with a matrix with linear initial part, okay? For instance, you consider a matrix with linear entries. Then in this case, we have this expression here, which is just a sum and a product of binomial coefficient, okay? Just a remark that even in low dimensions, it's not so easy to compute this kind of volume, okay? You can also count with the help of Oscar, okay? Here I have an example with linear entries. Then in this case, the local Euler obstruction is equal to -1, okay? Now, I don't have much time, but so I'm going to skip this. But if you remember, here, we ask for this condition that the Newton polyhedra should be convenient, okay? But we can also work with matrix which don't necessarily have matrices which are convenient, okay? In this case, we can use the ideas presented by Cauchy-Nerenko and the G-equivalence of matrix to prove this result. So, if we have a matrix which is Newton non-degenerated, but with non-convenient entries, then using Cauchy-Nerenko idea, we can add to the entry of this matrix this polynomial here. So we can get another matrix. And this matrix now, it is convenient because here this polynomial is going to touch all the coordinated axes, okay? And it is possible to prove that if this matrix is Newton non-degenerated, then this matrix is also Newton non-degenerated. Then our theorem says let X, A-n, be an isolated determinantal singularity defined by the matrix A with possible non-convenient entries. If the matrix A is Newton non-degenerated, then the local Euler obstruction of this variety at 0 is given by this expression. Here, it's more complicated because remember that the first formula here, okay, the Newton polyhedra is constant, does not depend on the row, okay? Now in this theorem, they can be different, okay? So here we have more complicated polyhedra, but this is the notation for the mixed volume of the polyhedra which are going to appear, okay? It is also a volume of polyhedras associated to the entries of the matrix, okay? And the M, which appears here, is greater than the determinants bound of A, okay? So, because here we are using a result from Pereira and Ruas. They prove that as isolated determinantal singularity is G determined. So, in this case, this matrix is going to be G equivalent to this matrix. Then they are isomorphic, and then they have the same Euler obstruction. So in fact, the formula computes the local Euler obstruction of the variety given by this matrix. But it is equal to the local Euler obstruction of this variety, okay? Now, what is important here, as I told you before, it is difficult to compute this volume by hand, okay? But what it is important here is that we have, for instance, a family of determinantal singularities with isolated singularities, which are Newton non-degenerated and which have constant Newton, if the family has constant Newton polyhedra, then the Euler obstruction, it is constant. It doesn't change because of volumes associated to the polyhedra, and the polyhedra are not going to change. So, as Ballesteros told us on Monday, for isolated determinantal singularity, I'm going a little fast here. For isolated determinantal singularity, we have an invariant, which is called the vanishing Euler characteristic, and which is a kind of generalization of the Milnor number for this class of variety. And as Ballesteros told us on Monday, this invariant has a Legros type formula. Okay. What we have here is the topipolar multiplicity of this variety, and P is a generic linear formula with respect to this variety. Okay. And why I am talking about this? These have to do with as we saw here, in the case of isolated singularity, the local Euler obstruction is given in this way, okay? But Ballesteros, Oref Sokamoto, and Tomasella, they prove that this is equal to the vanishing Euler characteristic of this section, okay? So here, in the Legros type formula, which appear, we can change this for this expression with the local Euler obstruction. So we have a family of Newton non-degenerated determinantal singularities with constant Newton polyhedra due to constant. But we can also compute this invariant using volumes of Newton polyhedra. And this is also going to be constant. Then the topipolar multiplicity of this family is going to be constant. And as you know, this invariant is very important and is related with the study of AX singularity, for instance. Okay? So, well, it is this. Here I have the references. And thank you very much. Feliz cumpleaños.
Okay, thank you very much, Thais. There is any question?
Some determinantal varieties are also toric varieties. So in that particular case, your formula, could it be simplified or expressed in terms of toric information?
Well, this is a very good question. I don't think on that, but probably yes. Because, for instance, in this example here, this matrix, the determinantal variety produced by this matrix is equivalent to the determinantal variety produced by this matrix. Okay? Because this matrix is G equivalent to this matrix. Okay? And the toric variety, the determinantal variety produced by this matrix is a toric variety. Okay? Yeah, I don't know. It's an interesting question because for the toric variety, we also have a Newton polyhedra, which can also look for this thing, but I never try to do the relation. Thank you for the question. It's an interesting question.
Okay. No more question? Comments? Okay. Thank you very much again. And the next conference is in 10 minutes.
So just a quick notice again. Since we believe everybody's going to be tired for the poster session before the lunch, so we move it after the lunch. Everybody has relaxed already, and then you can speak about mathematics without the empty stomach, so it's better.
Okay. Thank you.
Bueno, excelente. Creo que ahí está. Sí, para que no.
Ah, y aquí está la...
Okay? Okay, will be to continue. Okay. Okay. Then it's a pleasure to introduce Professor Juan Pablo Navarrete from the University of Yucatan. And he will be talking about limit set of air function group in PNC. Okay.
Thank you very much. I want to thank the organizers for inviting me to be here in this Congress. It's an honor to be here. Pepe was my thesis advisor, and I'm very grateful to him. So I'm going to talk about limit sets of real function groups in PNC, the n-dimensional complex projective space. This work is based on a work made with Valdemar Barrera y Eduardo. There are natural injections from the group SO plus 2,1 to SU2,1 and to SL3C. So when you consider a discrete group of SO plus 2,1 acting in the projective, in this way you can consider a subgroup gamma of SO plus 2,1, a discrete subgroup, as acting on the complex projective plane in such a way that it leaves invariant the Ball model for complex hyperbolic plane. Okay? And in the same way, or also, it leaves invariant this geodesic, totally geodesic space that is obtained as the intersection of the real projective plane with the ball H2C. In this talk, we assume that the limit set of gamma, the classical limit set of gamma, is equal to the whole boundary of this real disk. Okay? And if you consider gamma as acting on the complex hyperbolic plane, you can see that the limit set is, the classic limit set is again this circle, which is a real circle. Okay? But when you consider the group acting on complex projective plane, the Kulkarni limit set gives closed gamma invariant set, a canonical choice of a closed gamma invariant set, where such that the action on its complement is proper and discontinuous. This limit set is defined by 3 pieces, as Valdemar showed you. But in general, it's hard to compute because it's defined for very general spaces. However, in this case, the Kulkarni limit set can be computed as the union of all the complex tangent lines to the boundary at infinity of complex hyperbolic plane in points of the classical limit set. Okay? These complex tangent lines can be defined as the projectivization of orthogonal complement of a null vector with respect to this Hermitian form of signature 2-1, the classical one. And the continuity, the Kulkarni discontinuity set of gamma is defined as the complement of this. Okay? If L of gamma, the limit set, the classic limit set, is a real circle, a theorem, a beautiful theorem by Cano, Parker, and Seade, show that this limit set is a 3-dimensional semi-algebraic set containing this Möbius strip obtained as the complement of the real disk in the real projective plane. Okay? And this Möbius band is the singular set of this Kulkarni limit set lambda, because it's the intersection of any 2 of the lines defining lambda. In fact, they prove a little bit more. They prove that if you take out this Möbius band out of the limit set, you obtain a fiber bundle of the real circle with fiber, a complex line minus a circle, which means that this set is homeomorphic or diffeomorphic to the disjoint union of two solid tori. So I'm going to make a draw to illustrate this. Okay, here it is. This is the way I understand it, and I try to understand it. You have the limit set lambda gamma equal to the union of all these tangent lines. Here I drew the boundary of the complex hyperbolic plane, as this is 2 sphere. In fact, it's a 3 sphere. And the real projective plane is this horizontal plane. And the real R circle, or the real circle, is the intersection of this projective plane with the boundary of complex hyperbolic space. The Möbius band is all this thing in purple outside of the disk. And if you take a point in this real circle, then it is represented by a vector with real coordinates. So this tangent line to the 3 sphere at this point is in fact the complexification of this real line, because because it's the orthogonal complement. Okay, it can be defined in this way. So this is, as I said, the complex tangent line at this point, and this is the intersection. This line here is the intersection with the real projective plane. So any two of these lines, complex lines H set, defined in this lambda set, will meet at a point in this real projective plane, because their intersection point is the intersection point of their corresponding real projective line. Okay? And conversely, if you take any point here in this real projective plane outside the disk, you can trace precisely two real projective lines, which complexificate to a complex tangent line. Okay. So there is something there missing, and as you can see, the complex tangent line is split in two pieces by this real projective line. One disk is here in yellow, and the other disk is here in green. As you move the point around this, you obtain this the composition. Okay. Cano, Parker, and Seade also prove that this discontinuity set has three connected components, and they give explicit representation of these components. And each one is being SO plus 2 invariant and diffeomorphic to an open 4 ball. The first component is defined in terms of a Hermitian cross product corresponding to the Hermitian form of signature 2-1. And it's obtained as those points in the projective for which this point is positive as a vector. Or this vector is positive, in fact. And union the real disk H2R. Also, they prove that the set of those points for which the corresponding cross product is negative is decomposed in two components. One is omega minus 1, and the other is omega minus 2. And the property that characterizes them is the third coordinate of this cross product. Okay? Because, in fact, this cross product has real coordinates, and it's a negative vector, so it can only have a positive coordinate or a negative coordinate in the third one. This cross, It's the cross product associated to the usual Hermitian form of signature 2-1. It can be defined in a similar way as in. Is the no? It's a cross. Okay. It is an find it on vectors from C21. Such that it takes a vector, two vectors, and associates another vector. Like the usual cross product in R3. And it has these properties that it's orthogonal with respect to this Hermitian product to W and to B. And the formula is very alike, is defined in terms of, like usually it's done. You just use V1, V2, minus V3. Like this. And you obtain the vector. Okay? And it was introduced by Goldman, right? So I'm going to make a picture of the component omega plus, those points in the complex projective plane that satisfies that this cross product is positive with respect to this Hermitian form. Since this inner product, or since this cross product is a positive vector, we paint it outside of the ball. It's positive. And since it has real coordinates, we paint it on the real projective plane. Okay? Since the points Z and bar Z are orthogonal to that vector, it means that the whole complex line determined by Z and Z bar Z is meeting this ball H to C. Okay? But we did not paint here the real, the complex projective line passing through Z and bar Z. Instead of that, I painted this M of Z point that is some sort of midpoint of generalized geodesic of the geodesic determined by Z and Z bar. Okay, in fact, it's an orthogonal projection. What else? In this other picture, I have painted the other corresponding two components. Okay? The other corresponding two components were given by those vectors for which this cross product was negative. Okay? And they were determined by the sign of its third coordinate. Okay? In this picture, I illustrate this line, complex line determined by Z and Z bar, as not meeting the ball, because the point, its polar point, lies inside this real disk. Okay? And also, I have painted the two components, the two components corresponding to the component omega minus 1 and omega minus 2. Okay? Finally, a third theorem in this beautiful paper of Cano, Parker, and Seade show that there is a natural projection map from the Kulkarni discontinuity set to the real disk H2R, which turns each of these sets, omega plus, and omega minus 1 and 2, into an SO plus equivariant fiber bundle over H2R. in fact. It's a ball, the fiber. A ball, and a ball, two real. And work is a generalization to the case when you consider m smaller or equal to n and greater or equal to 2. Here we have this, again, these natural injections from SO plus M1 to SUN1 and to SLN plus 1C. So when you took a discrete subgroup of SO plus M1, you can consider as acting on PNC and leaving invariant by, well, acting in PNC by holomorphic automorphism, and leaving invariant the ball model for the n-dimensional hyperbolic space, complex hyperbolic space. And at the same time, leaving invariant this geodesic, totally geodesic subspace. This is the way these inclusions are ruled by this identification I have here. And again, if the limit set of the group gamma is equal to all the boundary sphere of this hyperbolic ball, then when the group acts on complex hyperbolic space, the corresponding classic limit set is what we call an m-1 dimensional R sphere. Okay? So we want to know what happens in that case. And but again, here we have to consider, or we consider the group gamma as acting in complex, n-dimensional complex projective space. And theorem, and again, the Kulkarni limit set, as I said before, is hard to compute, but a theorem of Cano, Liu, and Lopez shows that Kulkarni limit set is what it should be, the corresponding generalization of what I said at the beginning, that it's the union of these hyperplanes tangent to the boundary of complex hyperbolic space precisely at those points of the usual limit set, where these hyperplanes can be thought as the projectivization of an orthogonal complement to a null vector. In particular, if the limit set is equal to the whole boundary of this real ball contained in this sphere, then the Kulkarni limit set is equal to the union of all these hyperplanes where set runs over this m-1 sphere. Okay? No, because they are hyperplanes. They must meet in precisely one point. And we have the following result, that when m is equal to n and gamma is a discrete subgroup of SO plus m1, and you consider gamma as acting in this real ball with limit set the whole boundary, then the Kulkarni discontinuity set of gamma acting on this projective space satisfies that is again a smooth fiber bundle with invariant with SO plus M1. Well, this is one of the results we obtain. And the other result we obtain is this one, that in the case when m is greater or equal to 2 and smaller or equal to n, and gamma is a discrete subgroup of SO plus M1, and consider again gamma acting on HMC with limit set the whole sphere boundary, and you take this injection I told before, then the Kulkarni discontinuity region of this inclusion acting on PNC has 3 components when M is equal to 2. That was the case made by Cano, Parker, and Seade. And it's connected when M is greater than 2. 2 connected components were eaten by the lambda set. Finally, this theorem that says that in the case when M is equal to N and both are greater or equal to 2, and we have the same setting as before, the Kulkarni limit set of gamma acting on this projective space is a semi-algebraic set again, but when M is greater than 2, then this set has no empty interior. Okay? And this didn't happen in the case when M is equal to 2. In that case, it was empty interior, right? So here I have a sketch of proof for theorem 1. This last one we saw. I ordered it with the inverse order so we can remember this one. So I'm gonna show that this lambda has no empty interior. Okay, so it's the union of all these hyperplanes defined by as orthogonal complements to null vectors in this sphere. Okay, and this is the way you can write it. But in this way, you can say that are the points in the projective space such that these vectors are orthogonal with respect to this Hermitian form for some vector in this with real coordinates with real coordinates and a null vector. V0, V0 is a null vector. Okay? Where a null vector I mean with respect to the usual Hermitian form. Okay? And this equation, or this implies that you can rewrite the set in this way, where HW, boldface HW, means this orthogonal complement to W. Okay? And since you have this equation, WZ equals 0, you can take conjugate to the whole equation and use that Z is a real vector to prove that this inclusion holds. Okay? And it means that this space, this vector space, as it contains null vectors, it is what we call parabolic or hyperbolic. Parabolic means that it's the Hermitian form restricted to this subspace is degenerate. And hyperbolic means that it is nor positive definite nor negative definite. And this one line is painted in red because here is precisely where we use that M is greater than 2. Because if this space is the orthogonal complement to this space. So if this is parabolic, this other is parabolic. If this is hyperbolic, this is elliptic, meaning elliptic that it contains only positive vectors. But the converse inclusion uses strongly the fact that M is greater than 2, because if you take the orthogonal complement of an elliptic space, then it may be hyperbolic or negative definite. No? But it cannot be negative definite because this set allow me to move. Well, yes, it cannot be negative definite because this set here has dimension greater than 2 when m is greater than 2. Okay, so it must meet the boundary circle of the boundary sphere. Okay, so I painted here these two possibilities for this span, this vector space, when it's parabolic and when it's elliptic, and its complement, its orthogonal complement when it's elliptic precisely meets the boundary of HMR. So any point you take here will be on the Poulcare limit set. And you can express this lambda set by these two conditions that define precisely when this vector space is parabolic or elliptic. Precisely is parabolic or elliptic if this determinant is greater or equal to 0, and this inequality here is included to exceptuate, to eliminate the case of the points in the real disk. Okay, so also the SketchUp proof of theorem 3, basically the projection given is the same that was given by Cano, Parker, and Seade in the case m greater than 2. And there is no projection from the other two other components because these two components disappear eaten by the Poulcare limit set. And finally, for the theorem 2, we take a projection from the n-dimensional complex space minus a singular set to the corresponding m-dimensional complex projective space, and we prove that lambda is the inverse image of the corresponding Poulcare limit set here in PMC. Union this singular set, and some similar things happen when you compute the omega set. Basically, this is the bibliography I use. Here it is. Thanks for your attention.
Okay, thank you, Juan Pablo. Sorry, since there are questions, comments? Oh, okay. Thank you very much again. The next conference is in 6 minutes. 6 minutes.
6 minutes.
6 minutes.
Like this, that over the discontinuity set, you have a fiber plane, two-dimensional fiber, right? And then when you go to the limit set at the boundary, can you imagine the fibers intersect? They become these H sub z's. So if you go to the limit set, it's not a fiber bump anymore because the H sub z's intersect.
Yes.
So it's like a picture. The vibration breaks
Sure.
down somehow.
In fact, Parker and Cano and they describe how these leaves fit when they approach to the limits. Right. Sure.
but it's too many of them. So let me just say that this talk is dedicated to Pepe Seade. So we'll start now. So there is this slightly condition, there is a little bit more manifolds. And you can think of as having some points that here that are kind of doing nothing but just combinatorics. They don't use for the action, they are used for just for the combinatorial. So there is this kind of two games, the action and the combinatorics. Okay, the condition is there, a mouthful. I won't go through it, but there is more manifolds than LBM, slightly more. You can ignore this fact almost. The things that the LBM manifolds have kind of these points that you use all of them to write the whole thing, and now there is these other funny points that are kind of dispensable points. I'll explain this more geometrically when I briefly talk about quantum toric. In any case, to these manifolds, we get an associated polytope. Situation is this. We get one of these manifolds because we got one of these lambdas. So one of these lambdas affords you a polytope, some polytope there, convex tope. Here, secretly, what happened is that there was a toric variety, and here there was some abelian complex group. This manifold. Then you had a polytope. You have a polytope, you feel the presence of a toric variety. Well, it's there. There is a map from the BM manifold to the toric variety, and you have this information. And when this polytope has a rationality condition, then here you know that with the arithmetic condition, this becomes a complex torus. But if you don't have the arithmetic condition, this unwinds and it becomes this kind of orchestrated foliation. And then the so-called canonical foliation of the LBM manifold. This manifold carries, it knows its foliation. So in many ways, this object and this object are the same, but of course this object only exists if this is rational, almost. So that situation, the definition of the polytope is fairly explicit. Here it is, given the lambdas, of the polytope, just given the lambdas. So I may be allowed to come to this. So just given the lambdas, I can give you the equations of the polytope. It's very explicit. Okay. So the foliation has an explicit formula. Give me the lambdas, I give formula for the foliation, totally canonical. N knows its foliation. From it, N knows its symmetries, and then it knows its foliation. It just knows it's there and knows which it is. So it's totally, really canonical, and really endowed with a foliation for free. You don't need to give it to it. Okay, so it's there. The formula's huh? It's extremely nice. You'll see it in a second. On the strata here, if I put the strata here, and every stratum, on every kind of face and that kind of thing, is linear. It's very simple. And again, there is this condition, this arithmetic condition. So, if then you get the toric variety. But if you don't have the arithmetic condition, then you get a quantum toric variety. That is a non-commutative space. So, but because I will not really use this, although it was used as inspiration for the work, but I will not really use this. I will just mention it very briefly. The thing is that a toric variety is an integrable system. A quantum toric variety is a quantum integrable system. It is a non-commutative space, but the way to formalize this and make it into a reasonable statement is to think of it as a very non-separated complex stack. And so if you think in that category of objects, then not only everything is very nice, but moreover, you get a very nice modular space. As you move the lambdas, and of course, several lambdas make give you the same thing, and you have to divide by groups, of course. But as you move the lambda, you get some nice modular space. So you get the modular space of toric, commutative and non-commutative spaces, or varieties. So the rational points of the modular space are the classical toric varieties, the ones that are, you know, Kähler, complex manifolds, algebraic, whatever makes your heart beat. But when you don't have the arithmetic condition on the lambdas, the arithmetic condition is on the lambdas. When you don't have the arithmetic condition on the lambdas, then you become a quantum Kähler manifold, non-commutative Kähler manifold. So it's no longer, at the C infinity, in the C infinity world, looks like a non-Hausdorff manifold. But then try to put the Kähler structure, etc., is there. And so you get the theory of quantum toric geometry. And the theory of quantum toric geometry has been developed by Katsarkov, Merseman, and Berhovsky. We have this theory. Quantum fans, we have all the rigamal, or all the technology to think of quantum toric geometry. And for a toric geometry, I could say it is a generalization from rational polytopes to irrational polytopes, from rational fans to irrational fans, and now I have a modular space of toric varieties, ordinary and non-commutative. Both commutative and non-commutative form a nice modular space. In fact, this is a complex orbifold, the modular space. The modular space of toric varieties is a complex orbifold, and Antoine Boisbas is kind of the world expert on its structure and compactifications, and etc., a student of LoRa. Very well. Again, but let me go back. Now, this is the context, this is the scenario, and I will do the mathematics of this talk. The modular space is Hausdorff is an orbifold, a nice orbifold. And in nice cases, a complex orbifold. Sometimes it's a smooth orbifold, but the dimensions are right and whatnot. Complex orbifold. Okay, and sometimes just a smooth orbifold. And the top thing, and we don't have the Harrer stability theorem. All these things we suspect are there. So the modular space, just like the classical modular space MGN, this modular space is MGN. And n is the number of indispensable points. These points, mysterious points, is just the number of mark points there. Just like here there were mark points, here there are mark points on the fan. And G is the genus in the classical case. In this case, the G is the combinatorial structure of the polytope. It's just the combinatorics. That's G. So there is this kind of thing that determines the topology that is called G. It used to be G, determining the topology. And then there is this kind of mark points on the fan. This is n, and when the numbers are right, you get a stable modular space, and you get an orbifold. So very nice. And the topology, we need the topologies. You know, Rita, Miguel, all these people, to study the topology of this modular space. It can be arbitrarily complicated groups appear there under group cohomology. So it's not trivial. It's complicated. Okay. But we can say many things about the topology of this space, but not today. So, today, I want to go back to the Humboldt lambda. That is the same information as X lambda, somehow, especially in the complex geometric information. But there is this non-commutative complex geometric information, and here is commutative. Commutative are important. So I may want to know the complex geometry of these other spaces. Well, the thing is that why not trying to compute that? So we set ourselves the task of thinking about H, P, Q of n lambda. this is the subject of this talk. This is Hodge numbers of non-algebraic manifolds. We have a huge machinery to think about Hodge numbers of algebraic manifolds, or Kähler manifolds even. But these are not only non-algebraic, they are non-Kähler manifolds. So I'd like to say something about these Hodge numbers, because this will give us information about the quantum toric varieties. Okay. So Dolbeault cohomology, well, you know what it is. You have the Dolbeault complex there, and then you compute these numbers, the dimensions of the cohomology spaces. You can think of it as a refinement of the RAM cohomology, especially for the young students that are taking my class on the RAM cohomology. And it's closely linked to topology. But a lot of the theorems that you speak are not true at all in the non-algebraic, non-Kähler world. Okay, so let's compute this. Well, essentially what we do is, you could try, people tried some approaches, but they obtained extremely unexplicit formulas, unfortunately, by this Borel spectral sequence kind of approach, kind of an obvious thing to try, because you have this kind of thing. You could try this Borel spectral sequence kind of thing, but this gives you very, very non-explicit answers. So, so Laurent set out his computational arms and essentially sort of check to Dolbeault spectral sequence, more very explicit. And well, you do what you do. You write some atlases. You do things. You use equivariance. You think power series calculations, that kind of thing. And now you consider the following. Suppose that you have the lambdas, and now for all the rest of the talk, assume that yes, they are complex numbers and we are in the plane for the lambdas. This is the diagram of the lambdas. So this is 4 lambdas, 5 lambdas, 6 lambdas, so on and so forth. And we will do a little bit, a tiny combinatorial object that would be called L is the number of sides of this lambda configuration, and SL is the number of opposite sides on the configuration. Opposite SL. L is equal to 4, SL is if L is equal to 5, SL is equal to 5. If L is equal to 6, SL is equal to 9. Okay? That's what it is. And now, this is the theorem. HPQ of an LM is that. And here you have SL. So you get an explicit formula for the Hodge numbers of all these LM given for these configurations on the plane. Well, that's nice, isn't it? But you would like to, Alberto, nice formula? Yeah. Let me just clarify a little bit this L and M thing. We have n bigger than 2m. Lambda is an n-tuple of vectors in Cm. And now that's n and m. And L is the number of sides of the configuration. So we have n, L, m. L is the number of sides of the configuration. M is that m that appears there. And so we have. And so the thing is that the Hodge numbers only depend on L and m, on nothing else. Although you have many, many structures and so on and so forth, even not in the same class. Well, but nice formula, very nice formula. You get that. But we would like to understand this formula. Dolbeault cohomology. Dolbeault. That's right. That's right. What's the number? Dolbeault. Yeah, you're absolutely right. Of course. Well, you cannot hope that if you're in the non-Kähler world, but Laura, do we get this? I don't think so, no? Yeah. Mm-hmm. Mm-hmm. Mhm. 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 Well, I don't, yeah, of course. That looked like a proof, but I have to think about it, yeah. That looks like a proof, trivial proof, in fact. Okay. But, huh? but I'm teaching that class. I'm teaching that class right now. Which should be trivial for me because I'm teaching that class to this guy, you know. So, well, there is a case that is a little bit against the grain. There is a case of an interval, but it's very important, so I will mention it. So where you don't really have a polygon, but just R1 and just an interval. And that case is important. Have the following situation where we have also a quadratic formula on combinatorial numbers. Observe that this is quadratic on combinatorial numbers. And in the case of an interval, we get what we call quasi-Hopf manifolds. M equals 1 is the Hopf manifold, and so on and so forth. Topologically, the quasi-Hopf manifolds are the Hopf manifold, cross S1, cross S1, cross S1, cross S1, cross S1, cross S1, and M equals 3, I suppose. So we have many copies of S1 topologically, but of course they have a variety of complex structures. Interestingly, the complex structure for this one is not easily connected to the complex structure for this one. You cannot write one from the other in by any easy process. Now we get something interesting. What we get is that if we write the Hodge number for M equals 1, the Hodge diamond for M equals 1, then we write the Hodge diamond for M equals 2, then we write the Hodge diamond for M equals 3, we get a beautiful thing where if we have a little window of 2 by 2, and we put it around a position, and we have all the numbers here, we get the Hodge number for the next one. And we put a little window, and we have all the numbers here, and outside we consider them there is 0. We get all the numbers here, we add them up, we get the Hodge number for the next one. So as we grow M, we get this recursion formula for the Hodge numbers, which it would be reasonable to expect if you think that the Hodge numbers are topological. So, well, we have this Hodge-Pascal pyramid where you have all are the Hodge diamonds, and then you have this recursive relation to get the Hodge numbers in the subsequent Hodge diamonds. So, in other words, we get this recursion formula for NLM. So, the NLM plus 1 is completely determined for NLM, and so we can take the minimum M, this, for example, the Hopf surface, and this one determines the Hodge number of all the quasi-Hopf manifolds that are no longer surfaces. They are of all sorts of dimensions. The dimensions grow and grow and grow. Nevertheless, this recursion formula is true. Very well, so we have this nice recursion formula as we let grow all these points in the fan. If we think of the Pascal triangle, the classical Pascal triangle, the best way to represent this kind of recursion formula that one gets in the Pascal triangle it's better to represent it with a generating series. So this is, if you write this generating series for this case, we can write a polynomial two-variable polynomial, and it's, some people write it by E, and is the Hodge-Deligne polynomial. And this is a case. And it has very nice properties in the algebraic case that turn out to be rather deep. In the algebraic case, E of x is additive. If these are varieties, and this is if you have the finite covering condition, you have this. It is multiplicative. And if you have a Zariski locally trivial fibration, it behaves like this. Very, very nice property. These properties, they are seldom properties, they are properties of the Hodge-Deligne polynomial, complex algebraic varieties. Yeah, the xi's are disjoint. If they are not disjoint, then you have this kind of thing. You have this kind of thing. Huh? Well, think of this as a stratification, you know. Think of this as a stratification. Yeah. I'll say it in a little bit better in a second. Hmm? This one is starting with a finite covering, yeah. Yeah, they could intersect on lower dimension things or on anything, yeah. Okay. Well, so what is our case for ELM? So if I have these LBM manifolds, NLM, L sides, CM, I have LBM manifolds, NLM, what is the formula for the Hodge-Deligne polynomial for the LBM manifolds? The formula for the Hodge-Deligne polynomials for the LBM manifolds is this one. It is the Hodge-Deligne polynomial of the LBM manifolds, LBM NLM, for L sides and CM. Here E is an elliptic curve, and everything else is explicit. So this is the explicit formula for the Hodge-Deligne polynomial for LBM. SL still appears here in this formula, of course, is this combinatorial object, the number of opposite sides on the polygon. And the E of an elliptic curve is, of course, 1 plus U times of an elliptic curve. The elliptic curve is algebraic, and we have this explicit formula. Because this polynomial only depends on L and M, it is a topological invariant, even though the input to compute this was use the complex structure, it is a topological invariant. And observe that for L equals 2 and M bigger than or equal to 1, well, we get the 2M case. Again, it's a little bit different because of it's the segment. But this is for the case of the segment and L to N to M. It's slightly different, but it's very important. That's why I write it down. So we have the explicit Hodge polynomials for all these LBM manifolds. Well, the first thing to notice is that the recursion formula takes this compact form. Now the form is, it says that every subsequent LBM manifold, even though they are non-algebraic, behaves motypically. Even though the fibration is only topologically trivial, but not by holomorphically trivial, not at all trivial. LBM manifold, Lm plus 1, so it's behaving motivic even though there is no motivic place to work here because it's complex manifolds and there is no hope to establish a motivic structure there. So, if you want to think about this more computationally, is that it's enough to compute this polynomial, and this is the beautiful for the LBM L minus 2. And then you start thinking, well, it is kind of behaving as if there were these left-sided circle and left-hand motivic circles, and you play with this. In fact, because, for example, the Hopf surface, we know it's a transform of the trivial elliptic vibration over the P1, one may be tempted to compute the log transform motivic term. Right here, quotation marks to indicate that I'm computing the motivic difference between the Hopf surface and P1 cross E. And I do get a nice polynomial that seems to be the log transform correction or classical log transform. So you can play this kind of thing and think about this, and then you start feeling more and more that there a motivic ring, but you can prove a motivic ring. So what is going on? I don't understand the question. I have meromorphic functions, yeah. I haven't thought about that at all, but we can do it later after your question. Mm-hmm. Mm-hmm. Yeah. Not about my lecture. Anyway, we have this K0 bar, classical. Again, I'm going back to the world. Because I feel it's the algebraic world, but it's extremely far from algebraic. What is going on? We don't know what is going on. So in the algebraic world, we have K0 bar. That is a so-called motivic ring of algebraic varieties. It's, if you remember cobordism theory, you'll feel the flavor of it. You have K0 bar to be the quotient of the Z generated by isomorphism classes of varieties, like this. And then you generate an ideal given by this relation. This is the difference of varieties, that is still a variety. The difference of two varieties is still a variety. And so you get this in the ideal J, and then for any closed subvariety, and then you form a ring. And this ring has turned out to have extremely beautiful and mysterious properties. Very, very hard. Unlike cobordism rings, these rings, we have no idea what they are. They are very, very hard. But they are very, but we do know many properties of this ring in the algebraic varieties case. For algebraic varieties, we know a lot of properties of this ring. And we have been working here as if this ring existed for non-algebraic varieties. In fact, I can say a little bit better the thing about the Hodge-Deligne polynomial. What the Hodge-Deligne polynomial is the universal morphism from K0 bar to K0 Hodge structures. Well, you can go all the way to K0 vector spaces, and then you get numbers, you know. But it is the universal morphism from K0 bar to K0 Hodge structures. So for a smooth projective variety, one has that this is exactly this, with this the canonical Hodge structure. And then this implies this thing that the morphism from K0 bar to the polynomial ring in two variables. This Hodge-Deligne polynomial is a morphism from K0 bar to the polynomial ring in two variables. But you have to go through Hodge structures. And you don't have to go through mixed Hodge structures, by the way, because of nice theory, because of Hironaka, really. You don't have to go through mixed Hodge structures. You can just go through Hodge structures. Okay. Now, and then we can keep playing with LBM manifolds. And here is the toric, here is the quasi-Hopf, here is the toric variety. And you can start getting all these motivic identities. They are all checkable. They are all true implicit calculation, but this ring doesn't exist. But they're all checkable. You pretend that the ring exists, you do the motivic calculation, you predict the correct formula, but this ring doesn't exist. And we would like to know why this is behaving like this. This is behaving like this, as if this thing existed for complex manifolds, even though it doesn't. These complex manifolds is nothing, it's the integers. They are too flexible. So, well, there is no interesting homomorphisms here because this is the integers for complex manifolds. So, you do this kind of calculation. You get very beautiful formulas. You get that in this non-existent motivic ring, you get this kind of formulas, and they are very, very nice. So you can. Huh? That's what we're going to do, but we have to be very careful. We are going to extend the K0 bar enough, and we're going to do that, but we have to do a little bit, just a second. So we get very, very, very nice formulas. Here we have the Calabi-Ekman formula, the motivic formulas for Calabi-Ekman. Why not? Formulas in a non-existent motivic ring, but they're so we write them down because they are nice and la. And we do very, very charming things there that I will not explain. And then starts to be very funny. Characteristic P starts to kind of raise its tail here, you see, because when you see the traditional Hodge diamonds, the only universal linear relations between Hodge numbers are, well, you know, flip and the symmetry. And those are the only linear relations for all the Hodge appear in the universe for complex manifolds. Like this, and these are the only linear relations. Universal Hodge diamonds satisfy this. They are the only ones. That's for the complex case. Nevertheless, for characteristic P, Serre in 1958 discovered an intriguing example that behaves, and then this blows our head, like the Hopf surface, like an LBM manifold. But this is a characteristic P object that doesn't exist in algebraic varieties. And there is K0 bar over the characteristic P, and you will get this. You will get this object discovered by Serre in 58, called S, that behaves exactly like the Hopf surface, but it doesn't live in the complex world, doesn't lift to the complex world. So now we are intrigued. You know, when we do all our calculations, we get exactly Serre linear relations for Hodge diamonds, as the additional, I mean, exactly the same that appear in characteristic P, exactly the same linear relations that appear in characteristic P. So this is this is the fact that, well, you know, what's going on? All these manifolds seem to be log transforms. So could we include the log transforms somehow and form the algebraic varieties, plug log transforms and do it? Could we do that? Something like that. These are generalized for log transforms, not the one that are used to appear in the literature, but the one that is necessary to produce all LBM manifolds, LBMB manifolds. This generalized log transform realizes all LBMB manifolds as log transforms. Well, but what is it about log transforms? We were thinking, you know, what is it? Well, it is the fact that, not true, it is the fact that that they only use one additional function, the exponential function. And then, now you get it, you know. Now you know, if you talk to your friends, the logicians, what to do. So, there is Bob IAPLI. Just believe there is various concepts of Hodge numbers. Ignore this if you want. And now, You talk to your logician friends, and then they know about quantifier elimination, and then they tell you what is an all minimal structure. And then, it's something, you see, there is the algebraic world, and then there is the complex world, but there is an intermediate world that was envisioned in the intuition of Grothendieck and realized by an army of talented mathematicians in the 70s and 80s and 90s. There are that is the so-called tame. Have this kind of name of tame algebraic geometry. It's not algebraic, it's a little bit more, it has more. It's not complex geometry, it's in between. And it turns out that all BM manifolds are live in the best, nicest universal without the Jacobians, the really good one, O minimal structure. There is some O minimal structures, the algebraic, these ones, one, and there is one more, and this one is a nice one. Big theorem in logic that says that this is an O minimal structure, that it meets this quantifier elimination. And there you are in the Brouwer universe of constructible objects that you have to do, everything is finitist and everything you construct, but it's not so far from algebraic geometry, and especially from semi-algebraic geometry. The kind of the same flavor of semi-algebraic geometry has this world of constructibility in logic, and we use that, and we say, well, we start adding this definable structure, all these finitist procedures all along the way. LBM manifolds live there, so we are okay, and so all these finitist procedures all along the way, and now we have beautiful definitions, you know, and we have deep theorems. For example, we have this theorem that says that if we add this definable structure, they are isomorphic analytic manifolds, then no hope. If I do, there is no hope. But if I add that structure, this is actually surprisingly true. And this allows you to do compactification. You need Hironaka in this universe, but fortunately people work very hard, and Hironaka in this universe is available. And now you have this new Grothendieck ring that we define. And all the equations I was getting were occurring in this new Grothendieck, in this new motivic ring. The O minimal definable R and X motivic ring. A mouthful, but it's there. It's there. And then, well, there is this classical theorem of Bittner telling you how to go from, and again here on singular things to projective things and generate the whole motivic ring. Well, we prove it. It seemed Philip Griffiths, when we first heard that we were trying to do something like this, told us that this was very unlikely to hold water. But we managed to get the proof of this theorem. It's true. And now our main theorems are the RAM, Apelli, Bot-Chern, and Dolboko homology induces motivic measures. They are motivic measures in the motivic ring of definable complex manifolds. And moreover, if I divide by the Tate motif or the morphic classes of compact complex. Thank you very much.
Okay, thank you. Only one question, please.
So that just coming back to the definability, so that these manifolds are definable, right? But not in a polynomially bounded structure, right?
No.
Or non-definable.
No, not definable in a polynomial.
They are not definable, even that.
They are definable
over there, and that is why they are not moisture zone.
That's right.
Because that if they were moisture zone, they could be definable in a polynomially bounded or minimal structure. Thank you.
Couldn't say it better. Yeah.
Okay. Thank you very much, Ernesto, for the beautiful conference. Okay, and thank you to all conferences of today.
Does LVM have to do with the final statement?
LVM are not, they are defined, or minimal definable.